Well, so today's presentation will be about the hydrofoil cavitation analysis using actually OpenFOAM. Well, the purpose of this tutorial is to guide you step by step in setting up a simple 2D simulation of an NACA hydrofoil and run the hydrofoil by applying an existing cavitation model, which is in the OpenFOAM library. Therefore, this tutorial is more for you to understand how we can do this without actually getting into much details in the mesh resolution and whether we could better introduce different turbulence model or even other maybe cavitation models that would be maybe better capturing and more accurate capturing the cavitation types that you can see on this screen, which is the cloud cavitation and the bubble cavitation. The aim of this tutorial is trying to see how we can actually using a 2D case to capture the last one, which is the sheet cavitation. Therefore, we are gonna go through the tutorial, and I will try to show you how interchange foam actually works for this case and what are actually the OpenFOAM files that we need to modify it. And at the end, we can see some post-processing how we do the post-processing and see actually some of the results, which can be, of course, later validated experimentally or with other CFD similar cases. So the hydrofoil that was selected was this Nicolas 0021 with an angle of attack of 20 degrees. And it had a span length of 219 millimeters. The reason for selecting this hydrofoil was mainly because we have actual information to validate the results, at least for the non-cavitation cases, using other CFD results, and because there are also other experimental results available by other studies. Furthermore, the choice for selecting this angle is because it's one of the angle of attacks which we notice that there is some difficulty from the round turbulence model that are applied to actually identify the exact experimental results, and we see that there are some discrepancies even between the different turbulence models. For this tutorial, however, as explained, we're not going to create the fully 3D mesh. However, I'm going to show you how we can use the 3D solids that we have there in order to generate the 2D mesh using the available OpenFOAM meshing tools that that are available in OpenFOAM. So the first thing is to create in the block mesh, which is to create the block mesh, which is the first step actually to define our background mesh, from which using later on Snappy hex mesh, we will start generating the final mesh. The input geometry, as explained, was this NACA 0021. And what we did is actually we split the STL files into the pressure surface and also into the suction surface. The background mesh, as already shown also in the previous presentation shown by Lou, includes hexahedral elements, and the boundaries of the background mesh, as you can see, can be actually fully or maybe partially define the outer shape of the final mesh. This is usually done for this kind of external surface simulation. Therefore, the background mesh position and the dimensions are very actually important to be set correctly. And the simplest way for defining the background mesh, as we said, is to run the block mesh. Here you can actually see the block mesh dict, and what you actually see here is we can define the names of the surfaces. As for example, here you can see the seam front surface, and also on the other side it's the seam back surface, and also we can define the boundary for the inlet face and the outlet face. And later on I'll show you that what we can actually do is changing these names from seam front to another name, and also assign this face as empty, since we are going to simulate a 2D case. As already I think shown before, we need to do a quite fine mesh around the hydrofoil, and it is, as we said already, it is important to set correctly the boundary layer meshing. This is usually done in the Snappy hex mesh, and it was shown before, and we can change and play around with the add layers control. Furthermore, what we can do is actually we can implement different geometries. We can create boxes around these existing hydrofoils, and these boxes we can actually further refine our mesh and set up the refinement regions. This is the Snappy hex dict file. As you can see, the castellated mesh should be set true. Also, the snap is set true, and the add layers again for setting the boundary layer is true. Of course, you can put everything. We can put the add layers to no, so it will be actually you have the option not to create any layers around this hydrofoil. As we said, we have two STL files, and you can see that this was added into this dict file, and of course you see that we have named the one NACA up and the other one NACA low. And again, I talked about my box and the local box. It's the one box which is less refined, and it's in a higher distance from the hydrofoil, and we have also the local box which is closer to the hydrofoil. Another thing that we have to say here is how we can actually generate the 2D mesh using the Snappy hex mesh. And as we said, we're going to start with the 3D geometry, since as we know that the Snappy hex mesh is used to generate 3D meshes. To generate this 2D mesh, we can use this utility here, which is called the extra mesh utility. And how it works by actually projecting a face into a mirror face. And to do that, in order to do these faces, need to be actually parallel, and the input geometry and the background geometry, which is done by the block mesh, need to have the same width. However, in case that the input geometry is, let's say, larger than the background mesh, then also this been automatically facilitated, and it could cut the faces on the background mesh. In this case, the input geometry will be cut by the two lateral patches of the background mesh, as you can see here. So before let's start also with the tutorial. I believe all of you had received the files in the Dropbox. Okay, so you should have these 3 files, and as we said before, we can have a look at the system, what is in there, and as we've seen, there is the control dict, the block mesh dict, and also the Snappy hex dicts included in the system. And also we have this create but patch dict, which I will show you later on how to use it, and actually what we can is we can use that to change the names of our phases of our computational domain phases. So what we can do is the first command is to create the block mesh, and I'm gonna open this in order not to avoid typing. Then, as we said, we can use this surface feature extract, which is the one that will create the eMesh files that is usually that is actually used by the Snappy hex mesh. And what is this dict file doing? I will show you in a while. Let's go back. Maybe I should say that before. You can see that one. So what it actually does is it takes the files that were created, this em.mesh, and actually what it has in there, it has the edges, and these edges, using the Snappy hex dict, this can be further refined if you wish. In this case, we have set it to a level 3. And also, we see that in the next slide. Okay. And after completing the surface feature extract, and we create these eMesh files, we can actually run the Snappy hex mesh, and actually we can create the Snappy hex around this hydrofoil. I will do that, and then we come back and see after we try to do some of the slides we have here in my presentation to see what's the mesh that actually was created. Moving on, I want to jump in a bit on the bubble dynamics, because the idea is actually to see cavitation modeling for this example. So the dynamics of a simple bubble that is subject, let's say, to a changing pressure field can be very good described by the Rayleigh-Placid equation. This equation actually is derived by the rearranging of the mass conservation equation for a symmetrical spherical bubble. And as you can see here, where, let me have my pen, where R is the bubble size, and we have the surface tension of the bubble. We have RL, which is actually representing the density of the liquid, and we have the viscosity, the kinematic viscosity of the liquid. However, in OpenFOAM, for simplifying things, you see that all the higher order functions here have been neglected, and as well as the surface tension factors have been also neglected. So the only thing that actually remains into this equation is the radius bubble velocity. Furthermore, I have to say here that that thermal effects are also negligible for in this code, and in case that someone wants also to kind of include any thermal effects, this needs to be done separately. So a little bit mathematics about the model. As you see, the model includes the mass transfer that is going on between the liquid and the vapor phase due to evaporation and the condensation. This mass transfer is governed by the transport equation that you can see here. And as you can see, we have the liquid fraction that is included here, and also the density in the liquid phase, and also the m dot in the mass for the mass transfer rate. In order to implement this in the interface change foam, the mass transfers need actually to be decomposed by the evaporation term, and also the evaporation term and the condensation term. And as you can see here, that's why we use a different kind of notation. We have the same MA minus, which is actually for the evaporation, and this term actually it is for the condensation. Again, rearranging a bit the equation and trying to move, let's say, from the mass to the volume, the equation will result as equation 5 reads. And by substituting the V dot, which is the volume rate in this case, and also the convention term, we will end up in OpenFOAM on having this actually represented in our equation. And as you can see here, this is an input value by the user. It is the PV, which is the saturation pressure for the liquid. And this is quite important because actually this is what triggers the cavitation, and also meaning that it triggers what will be the mass transfer between the evaporation and the condensation. So in the interface change foam, there are 3 different cavitation model. The one that we are going to see here is the Schneider-Sauer cavitation model. As you can see here, we have illustrated how the evaporation mass transfer is calculated, and also the condensation. And as you see here, we have these values, the CV, which is actually the coefficient for the vaporization. We have the nuclear fraction, and we have the liquid fraction. This A nuc here is actually calculated by the model. I will show you how. And the AL is also calculated again by the model. With regard now to the condensation, again, the user needs actually to add this CC, which is the coefficient for the evaporation. What the model let's say assumes is that we have a uniform distribution of spherical nuclei in the computational domain, as you can see here, and that the nuclei will grow, and also that means that the vapor fraction will also increase. But on the same time, by increasing this vapor fraction, the water fraction also decrease. But by reducing by dropping into the computational cell the water fraction, that means also that the concentration of the nuclei will reduce, meaning that there is less available nuclei into our computational domain, which can be further grow. This is actually a quite clever way on how to control how the cavitation, how the bubbles will grow and later on evaporate, meaning that we're gonna kind of lose in the beginning the water, the mass water into this domain, and later on this will be coming back as water again because of the condensation phenomenon. Now, in this equation, equation 10, you can see actually the nuclear fraction, and the user needs to add into the model this nuke, which is the initial diameter of the nucleus that is included into the water, and also what he needs to add is the bubble concentration number. Usually these two numbers for the model are kept always constant, and these numbers are actually been can be given experimentally and also by the different flow tanks that are, of course, as you know, using also different quality waters when running their experiments. Having said that, what using the A nuke and also the NB, the bubble radius now can be calculated. And by calculating the bubble radius and having included the A nuke, it is kind of easy to calculate this mass transfer factors that you can see here, which is again, the one is for the evaporation, equation 13, and the other one is for the condensation. I suggest at this point that you can actually have a look at the Jansson paper, because all these equations are pretty well explained there, and it is part of actually the course of Hakan Nilsson is giving in Chalmers. Now, a few more words about the interface change form. You can find there the header files that are containing the equations for solving the momentum equation, the phase equation, and of course the correction of the interface. As we said, the user has the option to take one of these three existing models in the interface change form, which is the Kunz model, the Merkel model, and the Schneer-Zauer model. There are differences in these models, and I think there are also described in the literature quite extensive. And one of the major, let's say, differences compared to the Schneer and Zauer model is the way that they actually calculate this A nuke that is later on being introduced in the mass transfer equations. Furthermore, the user has the option to introduce also his or her own cavitation model. And as I showed you before, in this paper here, there is actually a good representation how you can actually create a new model, this Zwart-Gerber-Bellamry cavitation model. And in case you want to kind of modify any other equation within the existing cavitation models, you have two options to do that. Moving a bit fast with what is actually included in the Schneer-Zauer model, as we said, you can find how this bubble radius is calculated, and of course, you will see how the volume fraction of the nickel in the computational domain is also calculated. We see here that for this equation here that there is a bound that the value should be always between 0 and 1, and this line actually is therefore ensuring that. And also this 001 PSAT is in order to let's say avoiding getting negative values in case the pressure is quite much reduced. And the only difference from what I showed you before is that we get the RRB, which is the reversed bubble diameter. And this is also introduced here. And finally, you can see here the mass transfer formulation for the different phases that we have. And of course, we have the alpha nuke, which I explained what this is. Now, for our calculations, we use the boundary conditions that were set were to 1.714 in order to have a turbulence flow which is 1.215, and the pressure that was set in the outlook was 3,764 in order to set that the cavitation number should be set to 1. Now, with regards to the omega, which is the specific dissipation rate, and the kinetic turbulence energy K, as we said, I think many times during these 3 days, this can be actually calculated by using the formulas that you can actually see here. And of course, you can even calculate the turbulence intensity, or even if you know it from before, you can set it into your model. Now, going back to the tutorial, let's check if it finished. I think it did. It's moving a bit slow. I think it's the other way around. Yeah. Yeah, I think that, yeah, I made a mistake and I executed the wrong one. Yeah, so in this case, let's create it again. You can use Snappy Hex. Okay, I forgot to write override. So the mesh will be actually generated, but usually this will take 20 to 25 minutes for this rough mesh that I have done. So in order not to lose much time on that, I will show you the what's happening after the mesh has been completed. And we can, so there is two options actually to run this. We can run it in parallel, but in order to run that in parallel, you need to modify this decompose part dict file. So in my case, when I have done the simulation, I have used actually 8 cores. So and you can use the simple coefficients, and you can change that from here. So this number should be always be the by multiplying form by 4 by 2, then we're gonna get this 8, and this is how we get this. Now going back what we can actually here is a finished results with the time steps, but um, because I made the mistake and actually I didn't run the correct one, I will say that you need to follow what is included in the Dropbox, and it's actually a step-by-step how you need to run this. What after you complete the Snappy hex override, then what you need is to extrude the mesh in order to create the 2D, and then you need to create the 2D patch. Because also I have done in the initial mesh was done actually uh, in meters. We have to transfer that we have to convert this in meters. It goes to millimeters, and we need to convert that in millimeters. We can use this transfer points scale. I what I usually do in order to kind of initialize the solution, I use this potential foam, and after this has been run, I run this by using actually, where is it? I don't have it here. I run this in parallel by actually using this MPI run command. You have to put there 8 and the interface change form. And if of course you want to create a kind of log of the time step that has been generated, and of course you need to add here parallel. One thing I want also to show here is the control dict. And what we have included here is actually the library for the forces. And of course, as been shown many times today, we had also to kind of include the starting time and the end time. I'm moving a bit down. We have set here also the functions in order to get the forces on the hydrofoils on the lower and the upper surface. And also what we added here is the forces in order to get the lift coefficient values and the drag coefficient values. It is important, I don't know if I done it, I think I did. For the lift coefficient and the drag coefficient, you have to set this number correctly. In this case, as we said, the angle of attack is 12 degrees. So that means that this needs to change in order to take this into account. And of course, the rho, it is the density of the liquid, and the chord length of our NACA profile should be also set. I think I made here a mistake and I had added 8.5, which most likely needs to be changed and needs to be at 1.7, which was the initial value for this case. And furthermore, I had the option to add the vorticity, the gradient of the velocity, and gradient of the pressure, the diversion of the velocity, and also the Q criterion. Of course, there are many other options that you can add here. For example, if later on you want to even calculate the friction coefficient, then you could add here the wall shear stresses for the NACA low and up surfaces. So this was actually the control dict. I'm not saving. And let's move on to show you a bit of the results that we had here. Yeah, what you will see when you finish, when the calculation finishes, that you're gonna have um, the post-processing files, which include the forces that I showed you, and also it will include this hydrofoil low and hydrofoil up. This actually, these forces contain the different force coefficient that you wanted to calculate, and also it contains the in the hydrofoil low and hydrofoil up contains the forces, the pressure, viscous, and porous that are acting on the surface of your hydrofoil. What I usually like to do is extract this data into MATLAB, and actually from there I can calculate the lift coefficient and the drag coefficient. As in this case, you can see, for example, for the calculated time, which was from 008 to 0248, which represent this region here, we could um, actually extract only for this region the results. And similar, what I've did is extracting from the parallel processors in order to see them in ParaView, these two regions from 1.2 to 1.6 and from 008 to 0.248. What the graph here is representing is the, as you see, the lift coefficient, and you see a kind of high oscillations in the beginning of the code, which is what we usually see, what we do when we do cavitation study. And after a period of time when the cavitation is becoming, let's say, cozy state, which is a sheet cavitation that it's oscillating, but it does not oscillating so rapidly as you can see here. We see that the sheet cavitation remains a bit more attached, and actually it repeats in smaller cycles. And the same actually you can see here for the CD, that this repetition is done in smaller cycles. Before opening ParaView, I'm gonna show you what actually I meant before. So you see that we have the formation of the cavity in the front, and because also we have quite a high separation zone here, there is a tendency for the flow to move up, and also we have kind of cavities that are created close to the trailing edge region. What these graphs here actually represent is the velocity profile for the different chord lengths. So it will start with a 14%, which is about here, and we move up to 97, which is close here. And as you see here is that there is quite a lot of oscillation in the beginning, in the start of the simulation. And later on, when the sheet cavitation starts, let's say, to be becoming a bit more steady, and it oscillates back and forward, then this actually has been kind of reduced. And I think this is better represented for this case, which is exactly for the same time step. You can see the change in the pressure coefficient, and as well as what you see here is the Q criterion, and you see how the how actually here the fraction of the water is kind of changing, and you see how the model even at some point it can quite well predict the cavitation regions that are being created after even the flow is detached from the hydrofoil, meaning that there is quite a lot of vorticity here, or there is even which is actually shreds out from the surface these cavities, and of course these cavities have been tracked a few, let's say, millimeters after the this hydrofoil. Of course, there are issues here also with the how long actually these cavities would remain in your computational domains. And of course, there are different options that you can use, and you're trying to change maybe the turbulence viscosity. That's what people and researchers do, and trying maybe to uh, reduce a bit the viscosity at this region here in order to allow less dissipation to come into the vortex here, and meaning that these cavities will be have the tendency to move a bit further on that direction. And yeah, this is the example I told you before. This is a case where you see there is not much going on here because the sheet cavitation is already steady. And so the phenomenon is more quasi steady now. There are, even though the flow has exactly the same initial condition and the same pressure field. However, after a few time steps, you see that the oscillation is becoming smaller and smaller. That meaning that uh, we are at the point where the cavity will remain on this hydrofoil. Of course, if we alter a little bit our initial conditions, which is u here, the velocity, or even the pressure condition, you will see immediately that this field here would instantly change. And again, most likely we're gonna have a repetition of the cycle that I show you for the lift and the drag. Um, I will move to the conclusion, but I will promise you that we'll see something also in the para view, and also how we extract some results from MATLAB. I think I also included the MATLAB file into the Dropbox link, and you can actually use that in order to extract the data from the post-processing folder. So what I try to present today is a step-by-step on how to model the cavitation around a 2D hydrofoil. I showed you how we can actually do the Snappy HECMEX even though we want to do a 2D case, and how we can actually set the STL hydrofoil geometry. Then I show you how we can use the Ran's equation that are applied together with the Schnur and Zaur cavitation model. And now it's time, I think, to see a bit of the post-processing results with the ParaView, and also present you how actually MATLAB works on that case. So going back. So what I did with MATLAB is, can you see first of all my screen here? I hope you do.
Yes.
Good. So it actually takes this hydrofoil law, it takes the forces, and again, for the upper surface, it takes the surfaces, the forces from the upper surface. And what we do is we calculate the lift and drag coefficient, and we, of course, trying to present the lift and drag coefficient for this case. By running that, okay, you can see here how I told you before the velocity is changing when in each time step for for the different, let's say, chord sections. And here you can see the lift coefficient together with sorry, I didn't show you that. correctly. You can see the drag coefficient and together with what's going on with the non-cavitation case, and as well as what's going on with lifting cavitation. As you see, as it was expected, when of course you have cavitation, the lift coefficient it will be quite significantly reduced because of the cavitation. But in the beginning, you see these spikes. That meaning that at some points the forces were quite a lot oscillating before actually we reached this steady kind of sheet cavitation where we have this repetition in a constant frequency of this cycle. And this is for the MATLAB case. Let's see here. I think I'm gonna show you the results that I've extracted from ParaView. Put this in the order. Okay. In this case, I think I had a load state. Let's load this for getting move on. And fortunately, I'm using also an older version of ParaView, and sometimes there are some problems with that. Yeah, I need to update this. So this is what I showed you before, and what I wanted to show you here is actually by having the computational domain, which is this one loaded, the foam12.foam, you can actually extract two blocks. The one block will be only, let's say, the surface of your NACA 2D case, and using that you can extract the surface, and later on you can generate the surface normal in order to compute using your calculator here the lift coefficient. Now using that, you need later on to integrate the variables, and what you will get is the lift coefficient for this case. And the same, as you can see here, can be done with a calculator, and you set again in this case the normal x, and you can calculate the drag coefficient. In a similar manner, you can calculate this part here, which is the CP, the pressure coefficient, and you can plot, let's say, the different CP distribution along your chord line. And in order to do this Q criterion images, what I usually do is I extract the internal phase as a different block. Then for this case, I've done the slice in the Z direction, so it cuts actually well in that direction, in the Z direction, and it actually represents your NACA profile on this Z direction. And what I did is changing the threshold values for the alpha water, so meaning that I want to present here for a fraction from 0.1, let's say, to 0.8 in this case, and later on what I did is using the contour. What I've done is added the different value range for Q, and you can see these values represented here. Doing that, you will see also how this here is, let me run it a bit. It's moving a bit slow, I think. Yeah, it's moving slow. So yeah, so you get the Q criterion, and what you actually can see from this is the quite high separation zones in the beginning of this simulation, and of course, as you can see here, that due to the cavitation, also the separation zone compared to what we have for a non cavitating case is actually moving a bit more in the leading edge rather than close to the trailing edge for this case. So it's running a bit slow, but that's it.